Hi everybody, my name is Michael. Today I'm going to be presenting a study we performed at JPL, which looked using Ingrid and her co-authors' latest data set and actually searched all temporal sequences within CTX to try to find fresh impacts. And also thank you to all my co-authors, Gary, Carrie, and Lucas, and Ingrid and her co-authors for making this possible. What is this study? So in the figure, as we just saw in Ingrid's presentation, we can see a global map of the confirmed fresh impacts. And these impacts, I believe, were all confirmed with HiRISE. And as I mentioned previously, this study looks to find new fresh impacts rather than these new ones, but we'll still be using all of these known fresh impacts, well, most of them, as we'll see later. Another important note is that the CTX global catalog obviously it's quite large. It has 110,000 observations, and all of those are quite large observations, so these impacts might just be a very small portion of them. And this would require a lot of time for planetary scientists or graduate students to go through and find all the fresh impacts. So the automated method that we use to achieve this and find these fresh impacts was to process the entire CTX global catalog through a machine learning pipeline that can detect fresh impacts and extract the truly new fresh impacts with before and after imaging, where the first image, of course, does not contain a fresh impact and the second one does. And like this is a small example. I think Ingrid shows one in her presentation too, of a before and after image. So why do we care about fresh impacts? So Ingrid gave a lot of few nice details, completeness, better statistics, and so on. I'm going to also mention another one. So the InSight is a lander that recently arrived on Mars less than 2 years ago, whose objective is to detect seismic activity to help geologists learn more about the internal structure of Mars. If we can detect a new fresh impact and know approximately when it hits the surface, we might be able to link it to seismic activity, which could be very beneficial for the InSight mission. And yeah, so the context camera was used throughout the study because it captures much wider swaths compared to HiRISE and allows us to makes it much more suitable for planetary mapping. And also another reason is that the CTX catalog covers 99% of Mars today. So for this study, we're primarily concerned with repeated coverage, so locations that are covered multiple times. This repeated coverage of Mars is not 99%, but to my knowledge is still quite high. And here are some just examples of fresh impacts from the CTX camera. Like we saw in Ingrid's presentation, this is a similar impact. This is the third example is one that reveals excavated subsurface ice. And the fourth example is one that reveals subsurface that is brighter than the surface and leads to this bright looking impact. Both interesting and less common impacts that we might want to find. So this is an overview of the system that we use to go from a global CTX catalog to new fresh impact sites, like we can see here, which is a temporal sequence of the site. So for the first step, we start with a global set of all CTX observations, and we determine which subimages to process. And for that, we can see this example here. What this is something called a sliding window. We can think of it as like a fixed box, or fixed window rather, that moves at fixed intervals across the entire image until it captures, until it goes through it all. And this is what's happening here. We can see that this black outline box corresponds to this location. And if we can see in tiny little text here, it has 1.0 confidence, which means that, which we'll get into in a second, which means that we're 100% confident that, according to our machine learning model, that the sub-image contains a fresh impact. So like we just talked about, so um, when we, for each subimage, we want to run it through a machine learning model, which is going to give us a confidence on what it thinks the probability is that the subimage contains a fresh impact or not. So it takes in an image as an input and outputs a confidence that it contains a fresh impact or not. Yeah. And yeah, for the next step, we cluster the images into sites. So just spatially cluster them and find sites that have truly new fresh impacts. And finally, we display some of these candidates on a web page that makes it easy for planetary scientists or graduate students to go through. And yeah, and then after this, we can send a request for HiRise to confirm if if this was an actual impact or not, and maybe get some more details about it. So now I want to just talk a little bit more about machine learning. So in order to predict if an image contains a fresh impact or not, we first need to train a machine learning model. In order to train it, we need images that contain both positive, so images that contain fresh impacts, and negative images that don't contain any impacts. So after we train this model, we can then make predictions on new images, a process we commonly refer to as inference in machine learning. And like I said before, this is going to take the input. This can take the image as an input and give us a confidence, which we can then, if it's above a certain threshold of confidence, then we can confirm that it's a fresh impact according to our model. So we need both positive and negative examples of the fresh impacts in order to train our model. For the negative set, we can just randomly sample from the CTX global catalog in such a way we can think of as sort of uniformly random sampling from a sphere, although Mars is not exactly a sphere. Even though one of these images may contain a fresh impact, many machine learning models are robust to this at what we refer to as noisy labels, which means that most of the labels are correct, but a small fraction may not be. And label in this case just means it contains a fresh impact or not. Um, and the machine learning model that we used is one of these models that is robust. So obtaining the positive set is a little trickier. If we look to the right, we can see exactly why. There's usually repeated imagery for impact sites. In some of the images, the fresh impact may not exist. I'll just wait until it goes. Okay, so it may not exist, and then the impact actually hits and our forms, and then it fades over time. So, the actual images that contain fresh impacts is dependent on time, since it's a temporal sequence. So we needed something to make sure that we weren't getting those images that contain no fresh impact or something that's very faded. So to do this, so the way we achieve this is to have a starting list. So in this case, it's actually Ingrid's data set that she just presented, a large subset of it. And what we did, so since this catalog contains a lot of high-rise images, at least in the data that we got it initially, we cross-referenced them, each of those images, to the corresponding CTX sites, so the ones with the same latitude and longitude or very close by. And then we just simply manually labeled these sub-images, and we kept the ones that looked like they actually had fresh impacts and saved it as our positive set. Okay, so in order to evaluate our work, we first did a test set. So this was actually the equatorial region of fresh impact detections from the, so I mentioned that we had a large subset from the Ingrid's catalog. We actually held out some of those, and essentially we held out some of those and used them as a test set. So this is the test set, the purpose of it was to see if our machine learning pipeline would generalize well to other regions of Mars, or yeah, regions unseen, because the initial, the initial map that we saw, I'm just going to go back to it quickly. Yeah, we can see that, like Ingrid mentioned, there might be some sampling bias with these impacts. There's no reason why we can't find one in other regions. So we wanted to see if it can generalize to more of the surface. And so since our data set is a little bit biased, we're more confident on the regions near Ingrid's initial global map. Okay, so this is just some statistics of the test set. We had about 400 CTX observations, and we ended up seeing about 2,600 or 26,000 sites that contained a prediction with greater than 85% confidence. And yeah, there was 12 million classifications made. So this is just only 400 examples, which is not enough compared to the global CTX catalog, which contains 110,000. So it was quite a challenge to get to that, but we'll see. Okay, this is just the 100 most confident images that came from the test set. And we can see that many of these images look like they might contain a fresh impact. So they look like something that we want to investigate further, at least to my knowledge. Okay, so like I mentioned before, due to the scale of the study, we had to use a supercomputer to process the global CTX dataset, and it took about a week to process. There was about 2 billion classifications made. So a classification was when we just input an image to the machine learning model and get the confidence, and that was made across all of the CTX observations. And this is just a graph showing the confidence threshold compared to the detections. And like we can see here that there's, if I can see that clearly, 500,000 images that contain over 0.99 confidence. Okay, so we also went over a way to filter the temporal sequences, which show a before and after sequence of the no impact and impact. And yeah, and then after we review these, then we can send these to HiWish, and we actually have an observation now that I think already got imaged. I'm not sure. I think we're just waiting on the results, or I think it's in line to be processed soon. Yeah. Okay, so the conclusion is that using machine learning, specifically what the model that we used is convolutional neural networks, which is commonly used for images. We trained a classifier to detect fresh impacts, and we used that inside of a pipeline that went through the entire CTX catalog and was able to detect new fresh impact sites. Okay, yeah, that's pretty much it. Yeah, thank you to everybody who helped, and there was a lot of help that we got from this study. So thank you to JPL and everybody mentioned here. I'm open to questions now.
Thank you, Michael. Very interesting. So yeah, it looks like we have a few questions in the chat, so I'll hand it over to Stuart.
First up is Catherine Niche. How does your model handle the changing lighting conditions over the course of a day?
So what we did was we normalized the images to try to counteract some of this changing in light. So the normalization means that we, I think, just subtract by the mean and standardize it so that these are scaled similarly.
I think it's more the question related to, like, are there changing shadows or other issues due to time of day or season or anything like that you have to account for?
We didn't really take that into consideration. Yeah.
If I could, maybe I could just add to that. I think that's not really necessary here, because what what Michael's tool looks for is actually an albedo change, not a topography. So you're not trying to like identify the rim of the crater, and shadows would mess it up. So we don't actually see too much variation based on lighting in these features. The other thing is that CTX mostly takes images at the same time of day, I think. So I don't think there's too much variation in that.
Yeah, the vast majority of CTX images are taken around, I think, 2 p.m. local time. The next question is, again, by Fred Califf. Have you considered using your machine learning on high-rise to detect fresh craters? The coverage isn't as global from a sampling perspective, but it might give a sufficient sampling across Mars.
Oh, yeah, so that's a good question. So the high-rise set is a different distribution, which means that there might be different, the images are essentially different. So our machine learning model is probably not going to be able to handle the distribution shift, which is what we refer to in machine learning, from going to these different cameras.
All right,
So
and there was a
you
second.
oh, sorry, you would probably have to train a new classifier to handle that.
Okay, a follow-up by Fred. How did the CTX Fresh Crater machine learning results look like, or what did they look like spatially? Was it similar or dissimilar to Ingrid's catalog?
That's a good question. I didn't really investigate that. I think maybe Kiri or Gary might have some more insight into that because I left my internship right before we did the global deployment. So do Kiri or Gary have any insight into that specifically?
If they do, raise their hand or put it in the chat.
Okay.
Meantime, I'll move on to the next one. This is from Michael Clear. Were you able to perform a recall or false positive analysis using a holdout subset from the training data set?
Yeah. We had a validation set which we used to compute various metrics, including the RC curve, and we use that to evaluate our classifier. And we also used the calibration holdout set, which we use to calibrate the confidence for the model.
Kiri Wagstaff wrote, great question. Generating a spatial distribution map of detections is in progress once the review process is complete. So that gets back to Fred's question about the spatial distribution. There aren't any more questions for the moment in the chat, so I will go ahead and ask a question. How does the uncertainty and the errors in the pointing for CTX throw you off? Because I noticed that on some of your the images, the set of 3 that you were looking at, those had offsets in the lat long.
Oh yeah.
So what kind of jitter, I guess, do you build into the detection?
Yeah, so there's not really a good way to handle that. Yeah, so of course what you're referring to is like a localization error, which is pretty common for CTX images. I think it would just require more fine-grained localization, and I think there are tools out there that might handle this better. We used a somewhat simple approach, and I think we used an ISIS localizer, which actually I'm not sure if there's something better than that for this, but yeah, so that wasn't something that we can implicitly or explicitly deal with. So yeah, hopefully that answers the question.
Yeah, I mean, I'll just put in a small plug is that I'm working with a couple other folks from SWIRI on building a fully controlled CTX catalog and mosaic. So that would sort of be an update on what Jay Dixon and the Caltech group have out. So stay tuned for a few years for that. Meanwhile, it looks like Anya Losiak asks, are differences in CTX image quality influencing your results? For example, in the image that you're showing now, again, the one on the far left looks like it's a much higher signal to, or much lower signal to noise.
Right. This, I think, is something that's available that we can actually find from the CTX data. We didn't filter out these bad quality images, but I think there wasn't that many that we saw in our training set, so we weren't too worried about it. We didn't take it too much into consideration, though, about the bad quality images.
All right, Michael Clear asks a follow-up. Were you able to estimate the false positive rate using a holdout test data set? ROCAUC score. Thanks. Clearly, Michael knows more about machine learning than I do.
Yeah. So that we use that to validate our machine learning classifier before we actually sent it to our test set. And when we send it to our test set, it's much more difficult to do that because we don't actually have labels. But yeah.
Okay. I actually kind of have just a interesting question.
Sure.
Has this technique found any craters yet that formed during InSight's period so far on Mars?
I'm not exactly sure. I think maybe Gary or Carrie might know more about this. Yeah, so if we look to this image, then we see that clearly it hasn't. But I think there's still a lot of results that are left. We have barely scratched the surface on the results. So yeah, but hopefully.
Okay. Yeah, it was just mostly interest, just to know if
Yeah.
InSight should have expected to hear something. So, yeah.
Okay, I'll just say, since we have another few minutes, Michael adds, it sounds like there's some follow-up work needed to generate a test set to actually estimate the false positive rate. Thanks, and interesting work.
Right. If in an ideal world we would do that, there's just quite a lot of data. Well, there's quite a lot of labeling that would require that. But I think it probably would be a good idea actually to get some more sense of the generalization error. But yeah, we didn't use a labeled test set. We did use a validation set, but that's a little different.
Okay, and I will just add that processing all of the CTX data in a week sounds nice.
Yeah, well, supercomputer, but yeah, still.